The year is 2154. Our planet has been ruined by environmental catastrophe. In the movie Avatar, greedy prospectors from Earth descend on the world of an ancient hunter-gatherer people named the Na'vi. Their home is a lush moon far beyond our solar system named Pandora. Could such a place exist? And could our technology and our appetite for exploration one day send us hurtling out to reach it? In fact, the supposed site of this fictional solar system is one of our most likely real interstellar targets, until a better destination turns up. Pandora orbits a fictional gas planet called Polyphemus. Its home is a real place, Alpha Centauri, the brightest star in the southern constellation of Centaurus. At 4.37 light-years away, it's part of the closest star system to our Sun. Alpha Centauri is actually two stars, A and B. One slightly larger and more luminous than our own Sun, the other slightly smaller. The two stars orbit one another, swinging in as close as Saturn is to our Sun, then back out to the distance of Pluto. This means that any outer planets in this system, anything beyond, say, the orbit of Mars, would likely have been pulled away by the companion and flung out into space. For this reason, Alpha Centauri was not high on planet hunters' lists, until they began studying a star 45 light-years away, called Gamma Cephei. It has a small companion star that goes around it every 76 years. Now it seems it also has at least one planet. That world is about the size of Jupiter, and it has planet hunters excited. Perhaps 2/3 of all the stars in our galaxy are in so-called binary relationships. That means there could be many more planets in our galaxy than astronomers once assumed. At least 3 teams are now conducting long-term studies of Alpha Centauri, searching for slight wobbles in the light of each companion star that could indicate the presence of planets. If they find a planet that passes in front of one of the stars, astronomers will begin intensive studies to find out what it's like. One of their most promising tools will be the James Webb Space Telescope, scheduled for launch in 2014 or 2015. From a position 1,000,000 miles away from Earth, it will deploy a sun shield the size of a tennis court and a mirror over 21 feet wide. The largest space telescope ever built, it will offer an extraordinary new window into potential solar systems like Alpha Centauri. With its infrared light detectors, this telescope will be able to discern the chemical composition of a planet's atmosphere. And perhaps whether it harbors a moon like Pandora. One prominent planet hunter predicted that if a habitable world is found at Alpha Centauri, the planning for a space mission would begin immediately. Here's that star duo seen by the Cassini spacecraft, just above the rings of Saturn. To actually get to this pair of stars, you'd have to travel as far as the orbit of Saturn, then go another 30,000 times further. Or put another way, if the distance to Alpha Centauri is the equivalent of New York to Chicago, then Saturn would be just 1 meter away. So far, the immense distances have not stopped us from launching missions into deep space. In 1977, the twin Voyager spacecraft were each sent on their way aboard Titan III Centaur rockets. After a series of gravitational assists from the giant outer planets, the spacecraft are now flying out of the solar system at about 40,000 miles per hour. They're moving so quickly that they could each whip around Earth in just 45 minutes. twice as fast as the International Space Station. Voyager 1 has now traveled over 110 astronomical units. That's 110 times the average distance between Earth and Sun, or about 10 billion miles. But don't hold your breath. If it was headed in the right direction, it would need another 73,000 years to travel the 273,000 astronomical units to Alpha Centauri. When it comes to space travel, we've yet to realize the dream forged by rocketeers a century ago. A Russian schoolteacher, Konstantin Tsiolkovsky, inspired generations of space visionaries with sophisticated ideas about multi-stage launch vehicles. He imagined the construction of space stations in Earth orbit, and eventually vast permanent space colonies. In time, he predicted, we'd evolve into a whole new species, Homo cosmicus. Since then, rocketry's greatest advances have centered on ways of containing explosive propellants and methods of maintaining stable flight at high speeds. The problem is that chemical rockets are just not efficient for long-distance space travel. To reach the speed needed to enter orbit around Earth, 17,500 miles per hour, the space shuttle must carry 15 times its weight in fuel. And that's efficient compared to some other rocket systems. And you'd need to be traveling more than 25,000 miles per hour to break free of Earth's orbit and go anywhere else. A NASA study showed that to send a space shuttle-sized craft to Alpha Centauri in 900 years would take an unbelievable amount of fuel, 10 to the 137th kilograms of rocket propellant. Suffice to say, it's more mass than is in the entire visible universe. While only a very tiny percentage of NASA's budget goes to advanced propulsion, there are some promising ideas on the drawing board. Rockets powered by nuclear fuel, or plasma, a supervolatile gas. Huge sails pushed along by the pressure of photons from the sun. Ion drives. But to reach Alpha Centauri within a human timescale, we'll have to go with the most potent fuel in nature that we currently know. It's the science fiction fuel of choice, antimatter. In James Cameron's Avatar, hybrid nuclear fusion and antimatter engines power a mile-long interstellar spaceship. At a speed of 670 million miles per hour, this vehicle makes the journey to Alpha Centauri in just 6 years. Antimatter really does exist, as the mirror image of the universe we know. It consists of electrons and protons, but with their electrical charges reversed. Whenever it comes into contact with normal matter, the two annihilate each other in a ferocious blast of energy. Large amounts of antimatter were created and destroyed in the fiery dawn of our universe, the Big Bang. But somehow, in one of the great mysteries in science, we were left with a universe whose visible substance is almost all normal matter. The universe still produces antimatter through powerful collisions, such as a jet from a black hole slamming into a cloud of gas. When matter and antimatter obliterate one another, they emit gamma radiation that we can then detect with instruments such as the Fermi Gamma Ray Space Telescope. Fortunately, black holes aren't the only way to generate antimatter. In giant labs, like the Large Hadron Collider, scientists accelerate atoms to nearly the speed of light and blast them together to expose their fundamental constituents. Small amounts of antimatter can be made this way, but it's incredibly expensive. With a dedicated facility, the cost of producing it might come down far enough to produce usable amounts. And that's the hope of one researcher. Dr. Gerald Smith has been working for over a decade to find a way to trap this volatile substance and store it in isolation from the rest of the universe. Smith and his colleagues have designed a trap the size of a cigar case. It sits within a tank filled with liquid nitrogen and liquid helium, designed to cool it down to 270 degrees below zero. Once injected into this trap, antimatter particles are suspended by magnetic fields within a vacuum as empty as deepest space. But the problem is that anti-electrons, called positrons, tend to repel each other explosively. That makes it tough to store more than a few at a time. This team now believes it may have discovered a pathway to storing large amounts over longer periods of time. Their solution lies in combining positrons with electrons, forming an element called positronium. In theory, with the right magnetic fields, these electrically neutral atoms might be held indefinitely. When released under controlled conditions, ultra-high energy antimatter beams could turn out to be ideal cancer killers, or lead to revolutionary industrial applications. Or perhaps, one day, they could power long-distance spaceflight. It wouldn't take much. Antimatter is so potent that it defies common sense. A chunk the size of a small coin could propel the space shuttle into orbit. Smith estimates that once in low Earth orbit, a human mission to Mars would take as little as 10 milligrams worth. The basic idea of an antimatter rocket is simple. A beam of positrons is released into the engine core, where it annihilates the surface of a metal plate. That creates an explosion that propels the craft forward. Another design uses a sail. A cloud of antimatter particles reacts explosively to its surface, propelling it forward. Short of traveling to another solar system, there may be good reasons to contemplate developing antimatter propulsion. A preliminary mission would speed beyond the orbit of Pluto, sending back close-up images of dark planet-like objects that ring the solar system out in the Kuiper Belt. A longer-distance probe could reveal new details about the Oort cloud, a vast realm of comets that envelops the solar system. Once out there, it could sample particles that make up the interstellar medium, or send back unique data sets on dark matter, the invisible stuff that makes up the overwhelming portion of our universe. To make it all the way to Alpha Centauri within 50 years, an antimatter probe would have to gradually accelerate to around 10% the speed of light. That's 67 million miles per hour. It would then gradually decelerate as it approached its destination. At those speeds, hitting even a grain of dust could destroy the spacecraft, so it might be best to slow the journey down to a century or more. It's safe to assume for now that we would only send a probe to Alpha Centauri if we discovered a habitable world. There may be other choices in our solar neighborhood. They include Proxima Centauri, a red dwarf star 4.2 light-years away that may be gravitationally bound to Alpha Centauri. Beyond that, not quite 6 light-years away, is Barnard's star. Or there's Lalande 21185, a red dwarf 8.3 light-years away. We already know it has 2 Jupiter-sized planets. There are at least 22 stars within 12 light-years of Earth. And any way you look at it, the first interstellar voyage will be a quantum leap for humanity. The urge to reach out to distant horizons, to climb the highest peaks, to push ourselves past our perceived limits, seems to be a vital part of what makes us human. Yet, explorers of old set off not just because it was there. At times it was greed, hunger, fear, or despair that propelled them outward from their homelands and allowed them to endure their long journeys. Whether we attempt to make this leap to the stars may come to depend on how we regard this planet. To the physicist Stephen Hawking, the journey is imperative. "I don't think the human race," he said, "will survive the next 1,000 years unless we spread into space. There are too many accidents that can befall life on a single planet." Indeed, we can't foresee the impact of wars, social upheaval, or the course of human civilization in coming centuries. But today, we can see the often conflicting trends that could one day propel us out into the interstellar void. On one hand, the technological advances that might make such a mission possible could revolutionize many other aspects of life on this planet. The ever-increasing rate at which numbers of transistors can be placed inexpensively on computer microchips has become a metaphor for the advance of all technologies in this century. From a few thousand transistors on the first printed circuits of the 1970s, computer chips now have billions etched onto their surfaces. Even that number could seem amazingly small in another few decades. Many observers forecast a steep rise, even an acceleration, in the pace of invention and basic research, and for whole new solutions to the problems of energy, food production, health, and more. On the other hand, major periods of scarcity may loom. In the 20th century, the world saw the largest increase in its human population, from less than 2 billion up to 6 billion. The world's population is now around 6.8 billion. It's expected to reach 9 to 10 billion by the year 2040, with the biggest gains in Asia and Africa. According to a recent UN report, the world will have to produce 70% more food by the year 2050, and at least that much more energy to sustain its population. The scarcity of just simple clean water in some regions is already frightening. Now throw in environmental impacts, like rising sea levels, or the spread of deserts linked to a gradually warming climate. The culprit, to most scientists, is rising emission of greenhouse gases like carbon dioxide since the start of the Industrial Revolution. This map charts rising temperature readings from the year 1885 through to the present. In some places they've gone up by as much as 2.5 degrees Fahrenheit. Computer models project the trend out to the end of this century. Depending upon population growth, energy use, and conservation, temperatures could rise anywhere from 2 to 11 degrees more. Will technological advancements allow us to halt the degradation of our natural environments and increase the carrying capacity of our planet? Will we find ways to mitigate the impacts of war, natural catastrophes, or political upheavals? No doubt, if or when we launch our first mission beyond this solar system, the occasion will spur reflection on who and what we have become as a people, as a planet, just as the first missions to the moon and our neighboring planets once did. At first, we'll send a probe designed to relay basic information on what's there. on a world whose light we have only studied from afar. As this cosmic emissary makes its way across the void, we on Earth will continue to struggle in our pursuits of happiness and prosperity, or of mere survival. When it arrives, we'll scan the data for evidence of a world like our own, one that may harbor life. How will our perspectives on that world, and upon our own, have changed?
We also now know that Saturn is orbited by over 60 natural satellites. The largest of Saturn's satellites is a moon called Titan. It is enveloped in a thick atmosphere, one filled with orange haze. In 2005, a NASA probe penetrated the veil of mystery and sent back the first images of the surface. The terrain looked amazingly familiar. Black lines branched out over the surface. They looked just like rivers. And numerous lakes were discovered. This was the first time any celestial object had been found with liquid on its surface. The more the probe investigated, the more Earth-like Titan seemed to be. It was at this point that scientists began to suspect that life might be present.
Maybe in the seas, more interesting things happen. Maybe you get self-replicating chemical systems, much like those that are the first steps towards living systems that were deep in our own history. So Titan gives us a whole new set of possibilities.
There's the possibility that maybe there is life on Titan that has somehow found a way to make use of all of these building blocks that the atmosphere is making for it.
However, the temperature on Titan is minus 180 degrees Celsius. Could life really exist there?
Well, how do we know it's too cold? Imagine you're living on Titan and you're looking at the Earth. You'd say, oh, there's a liquid, there's organics, there's energy, but it's too hot.
Titan has both an atmosphere and liquids. Could life exist there? This planetary body, very similar to Earth. Saturn's moon, Titan. Imagine the journey from Earth to Titan. If you could travel at the speed of light, you'd pass Mars about 4 minutes into the voyage. At the 30-minute mark or so, you would pass the giant ball of gases known as Jupiter. Then, some 70 minutes after departure, you would finally arrive at Saturn surrounded by those beautiful rings. Like Jupiter, Saturn is a large, gaseous planet. Finally, you'd reach Titan. With a diameter of 5,000 kilometers, Titan is about 3/4 the size of Mars. It's a moon the size of a planet. Fully cloaked in that orange haze, Titan's true appearance was not known until the 21st century. In 1997 saw the launch of the Cassini-Huygens mission. The Cassini orbiter, equipped with cameras and other instruments, and carrying the Huygens probe, was sent to investigate Saturn and its moons, especially Titan. In 2004, 7 years after liftoff, Cassini-Huygens reached the vicinity of Saturn, 1.4 billion kilometers from the Sun. Cassini then proceeded to enter into orbit around the planet and its satellites, and to commence scientific observations. It took this image of Titan. For the first time, Titan's true features began to show from under that thick haze. The day was approaching when we would finally be able to see the surface of Saturn's giant moon. In December 2004, the Huygens probe separated from Cassini and coasted to Titan. The target landing site was near Titan's equator. What that site would be like, no one knew. Titan's atmosphere is 1,000 kilometers thick. The probe entered it. Huygens deployed a parachute and drifted down, jettisoning its heat shield. This image, taken from a height of 152 kilometers, was Huygens' first view of Titan, which was still obstructed by haze. Huygens was shooting still images as it descended. Its microphone also captured the sound of the wind rushing by. This was the first sound recording ever made of an alien environment. These images of Titan's surface were taken by Huygens from 16,000 kilometers up. Black veins, like the branchings of a river, are visible. It does look as though they are flowing to the mouth of a river. Now, from 8,000 meters above Titan, it looks just like the sort of coastline we're used to seeing on Earth. Finally, the landing. This is an image taken by Huygens just after landing. What look like rocks and pebbles strewn about over a flat plain are actually chunks of ice. The surface temperature is minus 180 degrees Celsius. Atmospheric pressure is a little higher than Earth's, 1.5 bars. The horizon seems blurred by mist. This is exactly like some rocky desert landscape on Earth. High above, the Cassini orbiter continued its observations. In the equatorial region where the Huygens probe landed, Cassini discovered a strange pattern. Some sort of regular striping. Further observations found similar striations covering some 20% of Titan's surface. Ralph Lorenz has dedicated himself to investigating this strange striped pattern. He is trying to solve the mystery of Titan's stripes by comparing them to patterns he finds on Earth. This is the Mojave Desert in the western United States. Lorenz believes Titan's stripes are like the peaks and troughs of desert sand dunes. There are indeed real similarities.
It's remarkable somehow that despite the different gravity, the thicker atmosphere, and the different material that the sand is made of, somehow the landscape ends up looking almost exactly the same as many places on Earth. By comparing the shape of the dune and the interaction with the rest of the environment, we can get an understanding of how these structures formed. And for example, different shapes of dunes form in different wind patterns.
So the goal is to solve the mystery of Titan's stripes by investigating terrestrial desert dunes. Lorenz's first step is to send up a kite with a camera for an aerial overview. He's looking for a place that has a striped pattern like Titan's. Next, he mounts a dune buggy equipped with GPS. He wants to measure the heights of dunes and the angles of their slopes. The shapes of sand dunes change by the minute. Lorenz plants a stake with a streamer attached. In fact, he plants a whole line of them along this slope. This will show what sort of wind creates this type of dune. The wind is blowing from screen left, across a gentle slope. Then it swirls around, as if to carve out that slope to the right. So it's become clear that here the wind flows from the milder slope over and down the sharper slope. Lorenz believes that the stripes on Titan are also wind-sculpted sand dunes. A closer look at that image of Titan's stripes shows ridges with milder and sharper slopes, similar to those in the Mojave Desert. So Lorenz conjectures that the wind on Titan must have been blowing from left to right. The winds blowing on Titan's dunes, however, are thought to be weaker than the winds on Earth. The reason for that is that Titan's gravitational force is only 1/7 of Earth's. A relatively small action can produce a big result. So on Titan, effects similar to those seen on Earth are being produced by mild winds.
Titan is still an active world where, geologically speaking, processes are still happening. And the fact that we can see sand dunes, for example, suggests that the winds that move the sand around are still active, that we're seeing a dynamic planet, much like the Earth.
There was another unexpected aspect to those images taken by Huygens. Look closely at those chunks of ice on the ground. They are reminiscent of stones turned over and over by rivers on Earth. Sharp edges are worn down. They're rounded, like pebbles. So there may well be liquid on Titan. This discovery attracted attention and astonishment. Meanwhile, the Cassini orbiter made a surprising discovery of its own. Black spots and blotches were visible near Titan's north pole. Radar observations showed them to be lakes, filled with some liquid. They number in the hundreds, and some of them are huge. This is the first time liquid has been found on the surface of any celestial body other than Earth. The lakes are dotted with islands and fed by rivers. But with a surface temperature of minus 180 degrees, any water on Titan would have frozen. What liquid could it be in these lakes and rivers? This is it. Liquid methane. On Earth, it's normally a vapor, but at extremely low temperatures, it condenses into a liquid. Methane melts at minus 182 degrees Celsius. It boils at minus 161 degrees. In the 20-degree range between those two extremes, it exists in a liquid state. The temperatures on Titan's surface are just right for liquid methane. Methane is composed of one carbon atom and 4 hydrogen atoms. It's the simplest hydrocarbon, and it constitutes the bulk of the liquid in Titan's lakes. A portion of the liquid is ethane, another hydrocarbon with similar characteristics. Scientists at the Jet Propulsion Laboratory are trying to determine how Titan's methane lakes were created by conducting experiments here on Earth. Christophe Sautan is an expert on bodies of ice found in the solar system. This device is called the Titan chamber. With internal air pressure at 1.5 bars and a temperature of minus 180 degrees Celsius, it reproduces Titan's environmental conditions. Inside is placed a disk of ice, standing in for the terrain on Titan. They then release droplets of liquid methane onto the surface of the ice. The methane disappears immediately, absorbed by the ice, like water being swallowed up by a thirsty Earth.
So the big surprise, something we did not expect, is that when the methane falls on the ice, well, actually the methane got sucked into the ice. It gets absorbed. It doesn't run on the ice.
However, if methane continues to drip onto the ice, eventually it begins to pool on the surface. This suggests that wherever there are lakes on Titan, the surrounding ice must be saturated with methane. During its landing on Titan, Huygens measured the concentration of methane. That concentration gradually rose the closer the probe got to the surface. Then, the moment it landed, there was a sharp increase. It is thought that this was due to the heat from Huygens vaporizing the methane that permeates the ice. On Titan, liquid methane acts in ways similar to water on Earth. In June 2012, for example, Cassini observed a strange phenomenon near Titan's south pole. An oddly shaped mass seemed to be squirming about in the atmosphere. It was a cloud, swirling. A cloud made up of methane. On Earth, water is recycled as water vapor and rain. One of the factors prompting this is seasonal change. On Titan, the same sort of mechanism seems to be at work. Titan is tilted on its axis, some 26 degrees off vertical. The Earth has a 23.4 degree tilt. It's another point of similarity. Along with its parent planet, Saturn, not shown here, Titan takes 30 Earth years to orbit the Sun. The tilt of its axis gives birth to different seasons. At this location, Titan's northern hemisphere experiences the long days of summer. The northern hemisphere is warmed, producing rising atmospheric currents. Liquid methane on Titan's surface evaporates and is carried southward. Near the South Pole, it is winter. The methane gas is cooled, condensing into a liquid or even solid state. It can form clouds. Like that huge swirling cloud Cassini spotted. When it's winter in the northern hemisphere, the cycle reverses. Now the methane cloud forms near the North Pole. Underneath that cloud, methane rain begins to fall. Since methane is more viscous than water, its raindrops are larger, with diameters of about a centimeter. But as Titan's gravity is weaker than Earth's, the droplets fall more slowly, about 1 meter per second, like a soft snow on Earth. They soak the icy ground on Titan and form lakes. Wind blows, rain falls. When people could finally see Titan close up, they were astonished at how much it resembles Earth. In 2007, the Cassini orbiter spotted something truly peculiar on Titan's surface. A land formation, some 70 kilometers across, in the shape of a flower. What could it be? Perspective can be gained by combining images taken from two different points of view. A three-dimensional image of the topography emerges. That strange formation turns out to be a rugged mountain, featuring a 1,500-meter high peak. There's also a chasm that looks like it might be a volcanic crater. From that, one can infer a formerly active volcano. That volcano has been an object of particular interest to Jonathan Lunine, an expert on Titan's internal structure. He says that the volcano did not spew lava, Rather, it pumped up a mixture of ammonia and water.
One thing to remember is that when water is mixed with ammonia, it can stay liquid down to very low temperatures, down in fact to minus 100 Celsius. But at that point, within a few degrees of that point, the liquid is actually very viscous. It's almost like basalt. And so if that is what is flowing out on the surface, we would see very thick flows.
Lunine believes that under the ice beneath the volcano, there's an ocean. He came to this conclusion due to changes in Titan's shape. Titan completes its elliptical orbit around Saturn once every 16 days. During that time, it regularly feels the changing effect of Saturn's gravity. In short, it experiences tidal forces. At its farthest point from Saturn, Titan is almost perfectly spherical. But at its closest point, where Saturn's gravitational pull is the strongest, Titan grows fatter. Its diameter alters by as much as 10 meters. Lunine says that Titan can transform so dramatically because internally it is not made entirely of solid rock. Lunine's observations suggest the following picture of Titan's structure. The outer crust of ice is some 50 to 100 kilometers thick. The center is comprised of two types of bedrock. In between the ice and the rock, however, is a layer of liquid water. The bedrock generates heat, says Lunine, permitting the water to remain in a liquid state. This ocean layer is some 300 kilometers deep. Ammonia, present in Titan since its origin, has also dissolved into the water. It is thanks to this ocean layer that Titan can change shape so flexibly.
The interior is warm enough that really only liquid water is a suitable, stable material in that region. So we're pretty sure from the gravity experiment that Titan has a liquid water layer under its surface.
According to Lunine, the tidal forces caused by Saturn in turn stimulate volcanic activity. Tidal forces cause friction along the boundary between the ice and the subsurface ocean. The water heated in this way melts some of the icy crust. It builds up like terrestrial magma and eventually forces its way up above the surface. This ammonia-laden water flows out from Titan's volcanoes like lava. Lunine believes such volcanoes are proof of an underground ocean. Beneath Titan's icy shell, a whole new world lies hidden. Saturn has over 60 moons. Among them are Enceladus, ice-covered like Titan, and Hyperion, pockmarked with craters. Mimas has this huge crater. Those are just a few of Saturn's moons, but they all have practically no atmosphere. Only Titan boasts an atmosphere that extends as far as 1,000 kilometers into space. Actual measurements reveal that this atmosphere is 98% nitrogen. The rest is largely methane. Why is Titan the only one of Saturn's moons with a thick atmosphere? Solving that mystery through experimentation on Earth has been a preoccupation of Yasuhito Sekine. Sekine believes that Titan's atmosphere was generated by an extraordinary mechanism. The mechanism? Collisions with small celestial objects. Sekine is trying to reproduce that effect using a laser. When Titan was first formed, its icy landmass contained about 1% ammonia. So inside a vacuum chamber, a disk of ammonia water ice stands in for the young Titan. The laser beam enters from the left of your screen. It strikes a projectile, which then impacts the ammonia disk. That was the laser shot. Gases released by the impact are measured. One is nitrogen, released by the disintegration of the ammonia. Titan's thick atmosphere contains large amounts of nitrogen. According to Sekine's calculations, based on his experiments, repeated impacts by small celestial objects could have produced just such an atmosphere.
タイタンの地殻中にもともと入っているぐらいのアンモニアの量があれば今の 1.5 気圧の窒素の大気を作ることができるということを明らかにしました。重要な点はですね、大きい天体でないと大気を重力的に持てないということです。なので他の衛星たちは同じように衝突は起きたんですけど、それぞれが小さいがために窒素の大気を持つことができなかったと。
For example, Enceladus, one of Saturn's other moons, is merely 500 kilometers across. That is 1/10 of Titan's diameter. Saturn's other satellites are also small, with weak gravitational fields. So even if they've been similarly impacted, they haven't been able to hold on to any atmosphere. But did Titan in fact experience repeated bombardment by small celestial objects? Hal Levison uses computers to calculate the history of the solar system. He has advanced the revolutionary theory that some 4 billion years ago, the entire solar system was shaken by a massive event. Levison argues that when the solar system was forming 4.6 billion years ago, Uranus and Neptune were closer to the Sun than they are now. He inputs the location and size of the planets, and also of the small celestial objects that lie further out. Then the simulation begins. At first, the basic situation did not change much. But some 600 million years later, Uranus and Neptune were suddenly flung to the outer realms of the solar system.
Then out, okay? And that caused the giant planets to slowly spread. It was infinitesimal. You wouldn't have noticed it, but the orbits were slowly changing. And that continued until Jupiter and Saturn got to the point where Jupiter was going around the Sun exactly twice. Every time Saturn went around once, and that configuration is what set the whole instability off. Okay, so you went almost overnight from a time when, okay, there was a little bit going on, but not much, to this very violent period where all hell breaks loose.
The smaller celestial objects, shown here in green, had formed a ring at the outer edge of the solar system. But then the gravitational force of Uranus and Neptune violently scattered these objects. The result was that in the period from 4 billion to 3.9 billion years ago, the planets of the solar system encountered a barrage of small celestial objects. During this period, Titan also was hit repeatedly, developing a nitrogen-rich atmosphere. That made it a very special moon.
たった1億年とかそれぐらいの短い期間なんですけど、その間にですね、その 1.5 気圧という膨大な量の大気を作ることができたというふうに考えられます。 タイタンっていうのはですね、唯一人類が、初めて見つけた生きている天体だというふうに言えると思います。で、地球と同じようにですね、表面で液体が存在して、それが蒸発して雲を作って雨を降らしてというような循環が起きているのはですね、現在の太陽系の中では地球とタイタンだけです。で、その点において40億年前のその出来事というのは、タイタンにまさに命を吹き込んだと、生きている天体にしたという意味で非常に画期的な出来事であったというふうに思っています。
1977 saw the launch of Voyager 1. Its mission? To explore and observe the outer planets, from Jupiter to Neptune. This was its view of Titan. It was a close look, but still the moon was shrouded in a thick orange haze. However, even then, one scientist maintained that the haze held the secret to sparking life below. Bishun Kare has been trying to penetrate the mystery of Titan's haze since the early 1970s. He participated in the Voyager mission. He has focused on the haze as being itself a source of life. Kare introduces a nitrogen-methane mix into a sealed flask to simulate Titan's atmosphere. The flask is fitted with electrodes. Now Kare discharges them. This is meant to reproduce the effect of lightning or other energy surges on Titan's atmosphere. It's about 10 hours since the start of the experiment. A reddish-brown substance has become visible inside the flask. Kare claims that this is the very same substance as the haze enveloping Titan. So what happened inside that glass vessel? First off, the electrical surges split apart the molecules of nitrogen and the methane. Their atoms recombine with carbon and other atoms in all sorts of ways, forming a variety of new organic compounds. Analysis showed that some 200 types of organic compounds had been created in this experiment. Organic compounds are the materials out of which our own bodies are made. They are the building blocks of life. It was thanks to Kare's work that Titan came to be considered one of the celestial objects on which life might exist. The Cassini orbiter's close-up observations of Titan have come some 30 years after Kare's experiments. Will they confirm that Titan's hazy atmosphere has in fact given rise to organics? The INMS is a device that measures molecular mass. Cassini has used it to determine the composition of Titan's atmosphere. Cassini's data were streamed back to Earth, where they were analyzed by Hunter Waite and his colleagues. Waite led the team that designed the INMS instrument package carried aboard Cassini. Waite's lab was able to reproduce and confirm Cassini's data by utilizing the same INMS system. They could then analyze accurately whatever molecules or compounds the instrument had detected. The results were astonishing. Rendered in the form of a chart, each of the different molecules identified by Cassini is represented by its own colored area. Various organic substances were created in Titan's atmosphere, ranging from ones with a single carbon atom to more complex ones with 6 or 7 carbon atoms.
When Cassini sent back data, we found out that the upper atmosphere was much more relevant than we ever thought, that most of the chemistry seemed to be going on in the upper atmosphere, that very large molecules were being created in the upper atmosphere, way beyond our expectations. Titan is one of the best organic factories in the solar system.
Bathed in ultraviolet and cosmic rays, Titan's upper atmosphere is continually engaged in converting nitrogen and methane into a rich array of organic compounds. As these compounds collect in the lower atmosphere, they produce Titan's famous orange haze. Finally, they are precipitated with methane rain onto the surface as well. It's been 4 billion years since Titan's atmosphere was formed. During that time, it is estimated the organics settling onto the surface have created a layer dozens of meters thick. The dunes discovered near Titan's equator are thought to be a large deposit of these organics.
Now on Titan, the sand is made, we think, from organic material, and we think that material comes down and gets built up into sand-sized particles that are then accumulated by the wind to form dunes much like these.
Amidst this accumulation of organics on Titan's surface are substances of vital importance to the emergence of life. That finding was made by a young researcher with a specialty in organic chemistry, Sarah Hurst. Hurst has undertaken a minute examination of the organic compounds discovered in Titan's atmosphere. She's written her own computer program to do that. Based on Cassini's observational data, she faithfully simulates the composition of Titan's atmosphere and produces the same organics. Next, she uses her computer program to determine the molecular structure of every compound.
These peaks right here are the masses of the ions in the mass spectrum data, and then it's the number of carbon, nitrogen, oxygen, and hydrogen in each of those peaks. And so then what the code does is it goes through and compares this information to a list that I've given it of all of the amino acids and nucleobases that we're looking at. So here we have, at 136, we have the molecular formula of adenine, which is 5 carbons, that matches. It has 5 nitrogens, it matches. No oxygen, and then 5 hydrogens. So we know from this that we have the molecular formula of adenine in this sample.
Genetic information for all life on Earth is encoded in DNA. Adenine is one of its 4 major components, or nucleobases, and all 4 have been produced in Hurst's experiments. If these nucleobases combine in such a way that they create DNA, then a huge step forward will have been taken towards life itself. With this discovery, speculation mounted that Titan might actually be capable of harboring life. Life on Titan? It may in fact already exist. If it does, what would it look like? The search is on for the answer. Trinidad and Tobago form an island country in the southern Caribbean. They have a population of about 1.3 million. They also have one of the most unusual lakes in the world. It's called Pitch Lake. It contains not water, but naturally occurring asphalt. It bubbles up from an oil field that lies underneath, creating a lake of asphalt that's 40 hectares in area and 80 meters deep. Strangely enough, Pitch Lake is the site of fieldwork being done by astrobiologist Dirk Schultz-McCook. He thinks that Titan is the best candidate for the location of extraterrestrial life. He's come here to try to envision what life forms on Titan might be like. Asphalt, like methane, is a hydrocarbon comprised entirely of carbon and hydrogen. You wouldn't think this was a substance that harbors life, but Schultz-McCook says it actually does contain microorganisms.
Well, this is one of the few environments where it's similar to Saturn's moon Titan, where we know that we have hydrocarbon lakes on the surface. Obviously, Titan is very cold, so it's still different than from over here. But we do have the liquid methane and ethane, which are also hydrocarbons. And if we can find out what kind of organisms are living here in the asphalt lake and how they adapt to living in the hydrocarbons, we think we can get some ideas to how life could operate on a moon like Titan.
Asphalt contains almost no water.
Did you say that there's microbes in there?
Yes, there's microbial organisms in that liquid asphalt.
In this thing?
In this thing, yeah.
Like maybe 1, 2?
Millions.
Millions?
Yeah.
Genetic analysis identified some 600 new types of microorganisms living in the asphalt. Most are archaebacteria, related to the primordial microorganisms that live in extreme environments.
So for them, actually, it's a great environment, it's a great food source, and basically a never running out food source because it's getting supplied from deep down there.
On Earth, there are microorganisms that can use asphalt for sustenance instead of water. Schultz-McCook is convinced that in Titan's lakes, there must be life forms that exploit methane in a similar way. Another scientist, Chris McKay, holds that the methane lakes on Titan contain creatures so unlike Earth creatures that they exceed our wildest imaginations.
Think of fish living in water and ask them to imagine a bird which lives in air. They probably can't conceive of an organism that is so much denser than the medium in which it lives. Fish move through water by floating. So they would imagine a bird must float in the air.
We humans live in an environment called Earth. We produce energy by causing oxygen and organic matter to interact. That is our lifestyle. But McKay is arguing that on Titan, life forms would be based on a Titan lifestyle that makes use of what's available on Titan. Titan's atmosphere contains minuscule amounts of hydrogen and acetylene. McKay thinks that there may be life forms on Titan that exist by deriving energy from the interaction of those two substances in a methane environment. McKay says that life could very well already exist on Titan.
So instead of being small and round, I would guess that a single-celled organism on Titan might be big and flat, like a sheet of paper, to maximize its contact with the nutrients in this thin soup. So it's living in an environment where there's not a lot of food. So it's got to access the food with big area. And maybe on this area, it has active molecules. So it's like a big flat sheet of paper with little traps on it to collect food. To that life form, that will be the normal environment.
It was not until the 21st century that Titan's thick veil was lifted. Now that we're getting a closer look, what new discoveries await?
So Titan gives us a whole new set of possibilities, and there are for sure perhaps hundreds, maybe millions of worlds like Titan around other stars. Do those have life? Titan maybe can give us some clues.
If life is found on Titan, humanity's view of the universe will surely change.
The best place for me in terms of finding another type of life would be Titan. Because if we find it on Titan, then we know that it really is too. It's not the same as us. When we go to Mars, we may find life on Mars, but we won't be sure that it's not the same life as Earth. So my best hope would be we find life on Titan, because then I know that we found two completely different types of life. Then I can go on to some other science problem.
There is only one body in space that we know of, other than Earth, that has a thick atmosphere and lakes. Titan. If life is found on Titan, it will instantly increase the possibility that life exists in many other places in the universe as well. We may not be alone in the universe. We may have many comrades. The quest to find out for sure continues. Clues to solving that great mystery lie hidden on Titan.
In 2004, the Cassini space probe approaches the ringed planet Saturn and its 56 moons. It discovers something almost unimaginable, conditions that might support life. And if those conditions could exist so close by, what might we find in the next galaxy? On a planet just like Earth. For millennia, we humans have looked to the skies and wondered whether we're alone in the universe. Today, we're closer than ever to knowing the answer. Some scientists believe we'll get our first look at our extraterrestrial cousins in the near future.
I hope it's in the next 10 years, and I'm ready for it next week. So, the sooner the better.
What's more, we could find these aliens not on distant planets in unexplored galaxies, but right next door in our own solar system. Scientists are now honing in on proof that ET is out there and living on the most hazardous of worlds. Our safari will journey to 7 destinations in our solar system to see just where these creatures could be and what they might look like. These exotic lands are unimaginably harsh. Life as we think of it would perish in an instant. But alien life may be far tougher than we expect, as we're learning from a surprising group of living things right here on Earth. Until just a few decades ago, we were sure our planet was unique. It is the only one we've found so far that has nurtured the evolution of millions of species. thanks to its abundant sunshine, warm water, and protective atmosphere. We logically concluded that life needed each of those things, a conclusion that ruled out all other known worlds in our solar system. But then, biologists began combing some of the Earth's darkest and coldest places. And to their surprise, they found living, breathing creatures. Biologists call these organisms extremophiles. Some don't need light or oxygen. Others survive in tremendous atmospheric pressure. It seems life can turn up practically anywhere. Take Antarctica. After years of searching this arid, frozen landscape, scientists doubted they'd find anything alive. But in 1999, a team of explorers unearthed a rock from 6 feet under the ice. What they found amazed them. When they cracked the rock open, they found it teeming with tiny creatures. Here, at temperatures of 68 degrees below zero and 6 feet under solid ice, life had found a foothold.
Biologists have been increasingly discovering life, not kangaroos, but, simpler forms of life that live at very cold temperatures, very high temperatures, very great pressures, even in places where there's sort of a high degree of radiation. It turns out life is able to live in a much wider variety of environments on our own planet than we used to think.
And if life can survive extreme conditions, not just here at home, but elsewhere in our solar system, think of what this could mean.
Unless there's something extraordinarily miraculous about our solar system or our planet, then life has got to be extremely commonplace. I mean, there's got to be large numbers of worlds with life, and some of them would have cooked up intelligent life.
In the beginning, our Earth was as deadly a planet as any. Over the first billion years of Earth's existence, cosmic debris pummeled it mercilessly. The impacts turned its surface into a broiling, seething inferno where life was impossible. But once the solar system settled down and the Earth began to cool, water appeared, setting the stage for life. In 1953, researcher Stanley Miller proved in a lab experiment just how easily life on Earth got its start. He combined water with hydrogen, methane, and ammonia, components of the Earth's early atmosphere. Then he zapped his solution with an electric charge to simulate lightning. His results shocked the world. Miller had created organic molecules called amino acids, the protein building blocks of all living things. If lightning helped jumpstart life on Earth, could it have done the same on other planets? Galactic probes have now found the ingredients in Miller's experiment throughout our solar system, including one essential to life.
One of the requirements that every form of life that we know about on Earth has, every single one, is liquid water. We've used evidence for liquid water to kind of guide our search for habitable environments.
Our safari is headed to 7 worlds, some possibly rich in water, where scientists believe aliens might be hiding. While any life there might have begun much like life on Earth, how it looks now is anyone's guess. We begin in the world that has always fired our imaginations, the planet right next door, Mars. Of all the planets where we've looked for life, it's the one we've studied most. The scientist who may get the first look at Martians, if they're found, is Steve Squires, principal investigator for NASA's Mars rovers.
Mars has always had, among all the planets, I think, a special fascination for humans. For a very long time, we've known enough about Mars to know that it is probably the most Earth-like.
It may be the most like Earth, with an atmosphere and seasons, but we humans would perish quickly on Mars. Its air is thin, 40 times thinner than the air at the top of Mount Everest. And it sits in a bad neighborhood of our solar system, near an asteroid belt. Its atmosphere is too flimsy to protect it. Asteroids continually bombard its surface. Violent winds can whip Mars's sandy soil into storms that consume the entire planet for weeks and spawn tornadoes 8 kilometers high. Midday temperatures at the equator of 1 degree Celsius fall to -70 at night. David Grinspoon is a curator of astrobiology at the Denver Museum of Nature and Science. As he sees it, Mars would be warmer if it wasn't a planetary runt.
When I grab coffee on a cold morning, I know that a small espresso is going to cool off quickly, whereas a larger coffee is going to stay warm much longer. Large objects stay warm longer because their interiors are shielded from the outside where the cooling occurs. And planets are exactly the same way. A small planet will cool off early in its history. A larger planet like Earth will stay warm for billions of years, which makes it a better place probably to look for life.
Despite Mars's drawbacks, it has always fascinated scientists because its terrain seemed to give evidence that it might support life. Its dynamic landscape of mountains, volcanoes, and deep ravines is not unlike our Earth. To early astronomers, these features look like oceans and rivers, and even a system of canals, supposedly not just supporting life, but actually produced by it.
Percival Lowell in the United States observed these things and inferred that, in fact, these things were so straight and so regular in geometry that they had to have been the product of intelligent life. Okay? Well, he was right. The problem was the life was at the wrong end of the telescope. In viewing this thing visually through a telescope eyepiece, the human eye-brain combination started to connect things that weren't really there.
Lowell was not alone. Some scientists were shocked when the probe Viking 1 beamed back this image. Is that a human face? Perhaps produced by Martians in their own likeness? Until recently, we've never really known where to look in our solar system for extraterrestrial life. But we've always known what the aliens would be like once we found them.
Consciousness. I was on a table.
Usually, there is more than a hint of the Earthling in our aliens. Hostile or lovable, they tend to resemble mutant images of ourselves. As a senior astronomer at the Search for Extraterrestrial Intelligence Institute in California, Seth Shostak has spent his career listening for the radio waves of a distant alien society.
There's no reason to assume that they're going to look like us or even think like us or behave like us or have language. You know, you just have to look at the variety of life on Earth and you see that, you know, nature can come up with lots of different forms.
But if there is life on Mars, how could it survive in such extreme conditions? Since the 1960s, scientists have sent dozens of probes to the Red Planet. The first pictures of the barren landscape quickly dashed any hope of finding intelligent beings. But what scientists did see startled them. Though there's no evidence of Martian-made canals, there are signs that Mars actually may have had water. Some think the angry red planet might once have been blue.
You just have to look back a couple of billion years, 3.5 billion, 4 billion years ago. Mars had a thicker atmosphere, had water on its surface clearly. Maybe it developed life. And as it slowly went bad, you know, the life had to adapt.
Life may have adapted, not died off, because some liquid water may still exist underground. But with no surface water, frigid temperatures, and ultra-thin atmosphere, Mars is a planet only one kind of creature could love, an extremophile. Extremophiles thrive in the cruelest of places. To see where they might lurk on Mars, we head to the Valles Marineris, a massive rift in Mars's surface, 20 times wider than the Grand Canyon in places, and almost as deep as Mount Everest is tall. Lakes may have once flooded this valley, and those lakes could have hosted life. As the water dried up, life could have evolved to cope with the harsher environment. We won't know what these extremophiles are like until we find them. But they may resemble creatures that exist in extreme places right here on Earth. An unusual team of biologists, called astrobiologists, study Earth for the kinds of life we may find in outer space. Astrobiologist Rocco Mancinelli is on the hunt for Mars's extremophiles.
If it went beneath the surface, and some of it undoubtedly did, then what happened to it? Well, it formed brine pockets. So what kind of organism can live in a salty brine? A salt-loving organism.
Astrobiologist Chris McKay thinks he knows the kind of salt-loving creatures that might survive on Mars. Creatures much like those he's found in one of the driest, saltiest places on Earth.
The fundamental challenge to life on Mars is, in a sense, the fundamental challenge of life here in Death Valley. It's dryness. That is the hardest thing for life to adapt to.
Thousands of years ago, a salty lake covered Death Valley, just as lakes filled Mars's Mariner Trench.
Move in closer. This is still wet, a little wet.
This appears like a lifeless place, a big, flat, white, empty horizon. But yet, just below the surface, we find layers of algae and bacteria growing. They're living in an environment that in many ways is fundamentally different from the environment that we sense on the surface. Here you're in a place which looks lifeless, looks dead, and yet you dig down and hidden underneath, there it is.
Beneath the salt is a layer of hardy green algae that survive on the water and light that trickle through. The algae in turn feeds salt-loving microorganisms.
Here in deserts on Earth, dried, salty lake beds, we're going to find them on Mars as well.
Salty deserts are not the only places life might be hiding on the red planet. There are Mars's tremendous volcanoes, some of them 6 times larger than those on Earth. Astrobiologist Penny Boston studies the caves, called lava tubes, left over after volcanic lava has dissipated. Not long ago, we assumed caves like these were devoid of life. They get no sunlight, and no sunlight means no photosynthesis. But in lava tubes outside Albuquerque, New Mexico, Boston has found evidence of extreme life.
Because we know Mars has many, many lava tubes. And so here we have the opportunity to see how these formed and also to look at the life that inhabits them.
The extremophiles Boston has found appear to be thriving. They get their energy by feeding on the minerals in the cave wall.
So here we're up close to the wall, and you can see these white patches here growing against the black basalt. And each one of these is like a major city for these little guys. And they're all nestled in these little pockets in the basalt. And so these guys are permanently adapted to these freezing temperatures. They never see any light, and they get what they can find in the environment.
Are there creatures like these in the caves below Mars's volcano fields? Boston thinks so.
We are going to find life, and I just hope that I live a long and healthy life so that I can still be around to see that.
We may already have had our first glimpse of Martians, not from our visit to their planet, but from their visit to ours. 16 million years ago, an asteroid slammed into Mars and propelled a 2-kilogram rock into space. Amazingly, that rock sailed to Earth and came to rest in Antarctica. Inside, NASA scientist David McKay and Everett Gibson were amazed to spot the outlines of fossils. Water has carved small tunnels in the rock. And in these tunnels, McKay and Gibson found what they believed to be evidence of bacterial life.
These are little microbes, and they're dead, and they're fossils, or in some cases, we don't even see the forms. We see the footprints or the evidence that they were there.
Life from Mars? Maybe. The hunt is only just beginning. NASA plans to send a rover called Phoenix to Mars. It will study the planet's ice cap and probe 3 feet beneath the surface. NASA even has a plan to send human visitors. They may not meet the little green men of our imaginations, but they could encounter life in some form. What will it look like? It is likely to be a subterranean dweller with an ability to survive on little water. Perhaps an organism with a taste for minerals, like the creatures in the lava tubes of New Mexico. Even the smallest find would have enormous implications. Proof that life is not unique to Earth, but exists just next door. Our safari to the places in our solar system likely to harbor alien life now takes us past the asteroid belt on the far side of Mars. Here, Jupiter reigns. But this planet, the largest in our solar system, is fairly hostile to life, thanks to its toxic gases and overpowering gravity.
Not only is it pretty cold out at Jupiter, it's also, it's got this really thick atmosphere, tens of thousands of miles thick, and it's got ammonia and methane and, things used to clean the bathroom. But Jupiter has more than 60 moons that we know about.
At first glance, those moons would seem unlikely places to seek alien life. Their atmospheres are thin, and they are inhumanly cold. The temperature on Callisto is lower than minus 200 degrees Celsius. The scientific probes Voyager and Galileo have detected little on the surface of these moons but ice, with one dramatic exception. Io is one of the closest moons to Jupiter. When NASA sent Voyager 1 to Io in 1979, astronomers were astonished to find its surface roiling with giant volcanoes.
Io is the most volcanically active place in the solar system, just spewing volcanic material from its surface all the time.
What could be heating the interior of this frigid moon? Amazingly, it's the force of gravity from Jupiter. The giant planet exerts enormous gravitational pull on its moons. The closer the moon, the stronger the force. So strong, it can actually stretch their crusts. But some of these moons have elliptical orbits, so as they near Jupiter, the crust stretches towards it. When they move further away, the crust relaxes back towards spherical. This constant tidal movement creates friction deep inside, and that friction generates heat. It's like rubbing two sticks together to start a fire. The pull of Jupiter is heating Io from the inside out. Volcanic fumes and lack of water make Io inhospitable to life. But Jupiter's other large moons are more distant, close enough for Jupiter's gravity to warm them from within, but distant enough to remain calm on the surface. 3 of them look particularly promising as possible homes for alien life. The one furthest from the giant planet, Callisto. On its surface, Callisto looks like our moon, scarred and cratered by countless hits from asteroids. Those impacts may have melted the surface ice for brief periods, allowing life to take hold. But in 1998, the Galileo spacecraft detected a much more promising incubator deep beneath Callisto's surface. Radioactive rocks and tremendous pressure in its core generate heat inside Callisto. The heat may be melting its icy crust from below, creating a hidden ocean. And hidden oceans could mean hidden life. As we fly closer to Jupiter, we find its largest moon, Ganymede. Ganymede is also deeply scarred. Ridges rise above its surface. Those bright spots are craters as big as 5 kilometers across and likely to be lined with frost. But these photos offer the most compelling clues to where life here might hide. They show flowing glaciers, glaciers that resemble those on Earth. Ganymede's moving glaciers could also be signs of heat within. So, like Callisto, Ganymede could also have a hidden ocean, buried beneath as much as 190 kilometers of ice. The third moon on this leg of our alien safari is the most intriguing. It is called Europa, and of the 3, it resides closest to Jupiter. That proximity to the giant planet means Europa's core may be very hot, far hotter than Callisto's or Ganymede's. But its surface remains frigid, a potent combination for life, since there could be a temperate zone where they meet. Mammoth fissures scar Europa's thick crust of ice, a sign that ice is always shifting. On our own planet, we see the same cracks in the ice sheets covering the Arctic Ocean. Europa's crust may be riding the largest ocean in the solar system, an ocean twice as large as all of Earth's put together.
Now, those oceans, if they're there, and the chances are pretty good that at least some of them are, they've been sitting around for a long time, 4 billion years, a little longer, right? In 4 billion years, an ocean of water, do you think anything might have cooked up there? Well, it certainly seems plausible.
The environment in Europa's ocean is more or less as nice as the environment in our own ocean, as a place for living things to exist. Heck, things from planet Earth could probably live in the European ocean.
But Europa's oceans will be very cold, even slushy. And sunlight never penetrates them, thanks to an icy cover that may be 16 kilometers thick. We might never have thought life could exist here if not for a revolutionary discovery off the coast of Ecuador. Deep in the Pacific, biologists have found flourishing communities of tube worms, crabs, and even squid. These creatures are thriving despite complete darkness, extreme cold, and the pressure of the deep ocean. They feed on bacteria that take their energy not from the sun, but from chemicals erupting from the sea floor. We might find very similar volcanic vents on Europa, supporting their own web of life. To find out, NASA scientists would like to put a lander on the Europan surface. Some would like to send a cryobot, a robot that would melt the ice and release a probe into the liquid below.
That's not so hard to do. You just have to melt your way through. But you're going to have to melt your way through not a couple hundred feet, but maybe a dozen miles of ice. And send down a fishing line with maybe a video camera and a light bulb on it and look around.
In all that water, we can't rule out the possibility that very simple life forms have evolved further. We might even find creatures as advanced as some here at home. Most likely, however, we would find microbes. But even that would be a sea change in how we view the birth and growth of life. Europa was warm. What if the place is one of the coldest known? Or if its lakes flow with toxic chemicals instead of water? These are the worlds we find as our safari continues even deeper into space. As our safari in search of alien life sweeps by the ringed planet, Saturn, we can see the violently swirling gases that choke its atmosphere. We can also feel Saturn's gravity, weaker than Jupiter's, but still formidable. We'll keep moving. We're not likely to find living things here. Saturn's rings are also extremely inhospitable. They're made of rock and ice, as small as a grain of sugar or as big as a house. But Saturn has many moons, 56 that we've spotted so far. Our safari heads first to one of those moons, a tiny frigid satellite called Enceladus, just 500 kilometers in diameter. Here, gravity is very weak, a fraction of that on Earth. And Enceladus has hardly any atmosphere. It reflects back into space almost all the sunlight that hits it, making it the shiniest object in our solar system. Until very recently, we also thought Enceladus was too cold to support life. It appears we were wrong. In 2005, after a 7-year journey, the Cassini spacecraft approached the tiny moon and detected something that stunned the mission's principal investigator, Caroline Porco.
So this was the picture that just, grabbed us. Just was shocking.
Those are plumes made of water from a geyser. The geyser's steam and hot water hit the cold vacuum of space and explode into a jet of ice. With little gravity to rein it in, the ice cloud can grow as big as Enceladus itself. Porco has never seen anything like it anywhere else.
It's like a planetary explorer's dream to come upon a body like Enceladus. Those jets, those fountains, if you will, just spewing vapor and icy snow hundreds of kilometers above the south pole of Enceladus.
There's only one conclusion. Tiny, frigid Enceladus is piping hot within. Like Jupiter, Saturn's giant gravitational field tugs on its satellites, creating friction and heat within.
As far as we can tell now, it seems like an inescapable conclusion that there may be liquid water deeper down on Enceladus because it's warm. And the best models we can put forth right now to even explain the warmth, much less the jets, seem to indicate that you would get temperatures warm enough to melt water.
Heat, liquid water, even the furthest reaches of our solar system may contain the chemistry for life. What kind of creature could live in the steamy waters of a geyser? Thanks to hot springs back on Earth, we have some idea. At one point, we assumed nothing lived in the steam-driven fountains of Yellowstone National Park. But then, biologists discovered microbes in these waters. microbes that feed on chemicals dissolved in the water. Today, we call them thermophiles. The hardiest can thrive in boiling water. Could there be thermophiles on Enceladus? To find out, our safari takes us in for a close-up of this extraterrestrial Old Faithful. It's too cold for anything to live near the surface, but temperatures there are minus 165 degrees Celsius. But what about the hot water inside? In the ice plume above Enceladus, Cassini's probes have found carbon dioxide and methane, chemicals that could feed life below. Just as the chemical-laden springs of Yellowstone feed microbes living there.
We have a body that very, very likely has liquid water in its interior, has shown us already it's got simple organic compounds and, you know, a whole host of things that make it, I think, a major body of astrobiological interest in our solar system.
If Enceladus has been a shock, astronomers have been astounded by another of Saturn's moons, Titan. It may be the unlikeliest to harbour life. Titan gets only a limited amount of sunlight, about 1,000th as much as Earth. Probes sent to Titan have detected ice, but no liquid water. And at temperatures of minus 138 degrees Celsius, that ice is hard as stone. What could possibly make Titan a promising environment for alien life? Remarkably, Titan in many ways resembles the Earth, but not the one we know now.
Titan has turned out to be the body fantastic in the Saturn system, which is long suspected of having an environment at the surface, not only similar to the kind of environment we find here on Earth, even, believe it or not, similar to the kind of environment we had on Earth before the emergence of life.
Titan intrigued Carolyn Porco's team so much, they directed the Cassini spacecraft to send a probe there in 2005. It was the most distant surface mission ever conducted. The probe saw just ridges and plains. But a later flyover by Cassini spotted a shoreline. Soon, thousands of lakes came into view, at least one bigger than the Great Lakes of North America. It's the first time we've ever detected liquid on the surface of another celestial body.
Kind of looks like Minnesota, except the lakes are not water. They're liquid natural gas. But liquid natural gas is a liquid.
And that's not snow. Those are methane flakes. Like Earth, Titan has weather. But it's of a rather psychedelic kind. There are even methane hurricanes.
It's not water, it's methane, doing all the exact same things. Raining, evaporating, flowing in rivers. So you have something that is basically doing what water does on Earth. On Titan, only it's methane.
A similar scene may have existed on Earth 4 billion years ago, making scientists suspect that Titan could also be an incubator for life.
Chemistry does go on. At those cold temperatures, it's really slow. But Titan has had 4 billion years in which to do some chemistry, and maybe in that period of time, maybe something is cooked up.
It would have to cook up without liquid water, something we've never seen before. But scientists aren't ruling it out. The substitute could be the methane, so abundant on Titan. Used for fuel on Earth, methane was long thought poisonous to all life. But in 1997, researchers examined mounds of methane ice in the Gulf of Mexico, and they were astonished to find colonies of small centipede-like worms thriving amid the frozen substance. They think the worms may eat bacteria that feed on the methane.
In general, things that we think of as deadly, many of them are potentially lively. If you can figure out an evolutionary way to tap into that energy rather than having it destroy you, then it can be bountiful.
There could be one more complication for life on the surface of Titan. With only a weak magnetic field to shield it, living things on the surface could be exposed to cosmic radiation. But that might not be a problem for an extremophile, as we found here on Earth. Biologists have uncovered plenty of life near Chernobyl's contaminated nuclear reactor, and even swimming in toxic radioactive spills, actually feeding off the decaying molecules. It's possible Titan's life forms could do the same. To find life on Titan, we may have to dive into its methane lakes, where we might find chemical-loving bacteria. We may even find microbes resistant to radiation, not unlike those here on Earth at Chernobyl, living on its rock-hard ice sheets. Organisms that eat methane might give off heat, melting the ice, possibly creating another fountain for life. There's no doubt, life on Titan would be a strange brew. But we have yet to visit the most bizarre world where scientists believe life could exist, and it's much closer to home. Our safari of the world's most likely to harbor alien life has taken us far. We've visited frigid deserts, submerged oceans, and methane lakes. But the world we are about to visit may be the most extreme of all. For our final stop, we are turning back toward Earth, to Venus, our closest planetary neighbor in the solar system. If life can survive here, it seems it could exist almost everywhere. To reach the surface of Venus, we have to fly through a dense layer of yellow clouds, 64 kilometers deep, with a composition similar to battery acid. The atmosphere here is 90 times heavier than Earth's, too heavy for a human to tolerate. On the ground, there are extinct volcanoes and lava flows as far as the eye can see. They cover 85% of the planet's surface. It is hard to believe Venus once had vast oceans.
You basically had a runaway greenhouse effect, where as it starts to get warmer, the oceans start to evaporate, and then that puts water vapor in the air. Well, water vapor is a potent greenhouse gas, so that's what leads to the runaway. The oceans basically boil off, and then the CO2 all ends up in the atmosphere, and so today you have this very hot, hyper greenhouse planet.
With temperatures around 460 degrees Celsius, Venus is even hotter than Mercury, the planet closest to the Sun. Not a surface hospitable to life.
Life as we know it cannot exist on the surface of Venus, because organic molecules would just be ripped to shreds by the hot gases.
But we've stopped here, not because of what's on the ground, but what's in the air. In 1982, the Soviet spacecraft Venera 14 visited Venus. In the clouds, 50 kilometers up, it detected temperatures much cooler than on the surface. What's more, it found the molecules so critical for life, H2O. So far, every bit of water we've found beyond Earth is frozen solid. Only in the clouds above Venus have we found it in vapor form, a possible incubator for life. But Venus's clouds are also filled with highly acidic sulfur. Once, we thought nothing could live in sulfur. But scientists have analyzed some of the most acidic water on Earth, leaching from a California mine.
Watch your head.
In sulfuric acid strong enough to erode metal, eat through clothing, and dissolve human flesh, they found life. Acid-loving extremophiles. These organisms feed on sulfur compounds, like iron sulfide, eating the iron and emitting the highly acidic sulfur. Do extremophiles like these float above Venus? Astrobiologist David Grinspoon likes to think it's possible.
Maybe in the clouds of Venus there are some sulfur-based organisms. Sulfur actually absorbs ultraviolet light in interesting ways, and I'm just imagining that there's maybe some kind of photochemical reaction going on where ultraviolet light is actually being used to convert chemicals into some higher energy state, which then is basically being eaten.
What will these aliens be like if we do find them? They would have to tolerate high temperatures and enormous atmospheric pressure. They would also need to thrive in acid concentrations deadly to most life forms. Perhaps they might resemble a hardier version of the acid-resistant extremophiles in California's mine.
We keep finding that life lives in places that we used to think were inhospitable. So whenever we say, oh, it's impossible, you couldn't have life in the clouds of Venus, I think we have to be very careful because they might just reflect our own ignorance or our limitations on our own imagination, and maybe not real limitations on the ultimate creativity of nature, which seems to find solutions to these problems.
As our safari returns to the cool, blue, lush and lively world of Earth, we can see why we so revere its life-sustaining gifts. But, as we are learning, even the most extreme environments can harbor living things. Extremophiles may resemble the first version of life in our universe, and they could even be the most common. Could they have evolved further from these humble beginnings? Could intelligent life be out there as well? For more than 40 years, scientists at the Search for Extraterrestrial Intelligence Institute in California have been searching the skies for answers to that question. Astronomer Seth Shostak believes he'll know the sound of alien life when he hears it.
We have a couple of observing projects to try and find signals. The biggest one are our radio searches, and that's where we use big arrays of antennas, and we point these antennas at nearby star systems that we think, well, this is the kind of star that might have a planet that might be something like Earth. We point in those directions, hoping to pick up a signal that would tell us that somebody there is clever enough to build a radio transmitter.
It's a safari that never leaves home. Astronomers have also recently captured enough light from planets in distant solar systems to deduce their chemical makeup. They have found elements that may help form RNA, one of the building blocks of life here on Earth. And 20 light-years away, in the constellation Libra, a team of European astronomers has found a planet that could be warm enough to have liquid water on its surface, just like Earth. Meanwhile, headed to the furthest reaches of our galaxy are 4 spacecraft launched in the 1970s. Aboard 2 of them is a map of our solar system and the image of a man and a woman. 2 others carry a sample of uranium, whose rate of decay would date the probe, regardless of language. The 2 are also carrying what could be the most universal message of all, a recording that includes a composition by Bach. Just don't expect news anytime soon. These intergalactic postcards from the Earth will take 80,000 years to reach the nearest star. Our search for life beyond Earth has only just begun. There are billions of planets yet to be explored. Every one of them holds the tantalizing possibility of life. Even intelligent life.
Just in the face of this enormity, the idea that we're the only game in town, it just doesn't seem reasonable.
I think the question of whether we're alone is profoundly important for human beings in general. If you're aware, you really have to ask that question.
Somewhere in a galaxy known or unknown, something or someone could be looking out into space, peering at the Milky Way and wondering, Is there life out there?